Welcome to my third video of 3 on how to solve limits. Today we'll be talking about how to solve limits graphically. And it's a bit of a misnomer because you don't actually solve it graphically. It's more like you look at the graphs and they tell you how to then solve it. And you'll see what I mean. But what's important is that remember what a limit is. We're curious what happens to the y values as the x values approach a. And just keep that in mind through this whole video. Let's start with a really simple one. F of x equals x squared. And let's take the limit of f of x as x approaches 2. And now we know how to do this, right? We know that we're ultimately just going to end up plugging in 2 and squaring that and getting 4. But let's look at how to do it graphically. So what we do when we're solving limits graphically is that we literally just graph out f of x and do what we did when we were basically first looking at limits, right? Let's look at the x's from the left and from the right. So let's do that. We're going to draw a couple of x's coming at 2 from the left, or the left-hand limit, and we're going to do the same with a couple of x's coming at 2 from the right, or the right-hand limit. And we can see what the y's do, right? As the x's approach 2 from the left and the right, the y's approach f of 2, right, or 4, right? But the y's approach f of 2 from the top and the bottom. So what this means is that basically, since this is a nice, smooth, continuous function, as the x's approach 2, the y's approach whatever the function is at 2. So we can just plug 2 right into f of x and get 4. Let's look at one that is slightly more difficult, and this one is technically a piecewise function. F of x equals 2x plus 1, where x does not equal 3, and let's take the limit of f of x as x approaches 3. So what this is saying is that we have a function f of x equals 2x plus 1, and that is true. So our y is equal to 2x plus 1 everywhere except where x equals 3. So as long as x does not equal 3, f of x is 2x plus 1. Where x equals 3, the function technically does not exist. But as we've discussed earlier, that does not mean that the limit cannot exist. So let's look at how we would, quote, solve this graphically. Although this one looks a little different, we're still going to solve it the same way, right? We're going to look at what happens to the y values as the x's approach 3 from the left and from the right. So let's draw some dotted lines, a little bit less than 3, a little bit greater than 3, and let's see what happens to our y values. So this is why, quote unquote, solving limits graphically is a little tricky, because we can see what's going on here. We just can't quite put it into a formula, right? So we can see that the function does not exist at x equals 3. But if the function did exist at x equals 3, that's what our limit would be, right? Because as the x's are approaching 3, the y's are approaching that value. Because if it existed at 3, it would just be a smooth, continuous line, and we wouldn't have to worry about it. We know we could just plug 3 in. But it doesn't exist at that point. However, we know that the function does not need to exist for the limit to exist there. So we can look at this and we can see that the y values are still approaching what that value would be if x existed there. So we can just plug in 3 into 2x plus 1, and we get that the limit of f of x as x approaches 3 is 7. Let's look at one that's a little trickier. So here we have another piecewise function. F of x equals negative x minus 2 for x less than 0, and x over 2 plus 1 for x greater than or equal to 0. And we're going to find the limit of f of x as x approaches 0. So you see here we can't really use the previous method of solving limits analytically, right? We're taking the limit as x approaches 0, and it's a piecewise function, right? What are we going to try to factor? What are we going to try to rationalize, right? It doesn't work. And so that's why we have to kind of look at this and try to use graphs to figure out what we're going to do. And you might be able to see where this one is going, but just play along. So as x approaches 0 from the left and the right, we're going to do just as what we did before. Pick some values from the left and some values from the right and look at what's happening to the y values. So we do that, and as we look at what happens to the y values as x approaches 0 from the left, we see that it's going down towards -2, right? It's going down towards that bottom number. But as x approaches 0 from the right, it's going down towards a different value, right? It's going down towards 1. So the left-hand limit and the right-hand limit, they don't equal each other, which, if you'll remember, is one of our conditions for the limit existing. So when left-hand limit and right-hand limit do not equal, that means the limit doesn't exist. So since the piecewise function is broken at this point, the limit doesn't exist as x approaches 0. But now let's do one more problem. Let's look at the same piecewise function, but let's take the limit as x approaches 2. And so we know what to do, right? We look at what happens to the y values as the x values approach 2 from the left and from the right. So we draw little dotted lines, and we go a little less than 2 and a little greater than 2, and we're going to look at what happens to the y values. And we can just look at this, and this is why solving limits graphically is a little tricky, because you're looking at it and you're drawing conclusions from just the graph, right? This is a straight line at this part. And when we look at the y values, it's clear that as the x's approach 2, the y values are also approaching 2, right? Whatever the function is at x equals 2, that's what the y values are approaching as the x's hone in on 2. So just to be safe, we're going to plug in 2, and 2 is greater than or equal to 0, so we're going to use the bottom half of the piecewise function and get that the limit as x approaches 2 of f of x is 2 over 2 plus 1, which is 2. And remember, this is why solving limits graphically is a little tricky, because you're not actually solving them with the graph. You're using the graph to figure out how to solve them, right? In this example, we looked at the graph and we saw that, oh, at x equals 2, it's a smooth function, so we can just plug in 2. But previously, we saw, oh, well, at x equals 0, it's broken, so left-hand limit's not going to equal the right-hand limit, so the limit doesn't exist there. And in the even earlier function, when the actual point was missing at that x value, we knew that, well, the function doesn't exist there, but we can look at the graph and we can tell that the y values are still approaching that value, even though the function doesn't exist there. So that's why solving limits graphically is a little tricky. You're just looking at the graph, and the graph will tell you how then to solve the limit. If you found this video helpful, please like, subscribe, and I will keep the math content coming.